Thank you for joining us, and I'm going to present today about rebuilding the MSM software. Basically, I'm sorry I'm sitting right now, which I'm not used to because I'm presenting. But in this on level 9, this meeting room is strange a bit, so I'm presenting while I'm sitting. Okay, so what we are going to talk about is what I should do with the MSM, and my first task was to and this is a quotation for the notion that Emma prepared me before I started. So refactor MSM code, remove redundant code, unused code, improve speed with parallelization, and improving the interpolation method in general, and specifically in the MSM software. So what steps I took? So the first one was obviously to investigate. Yeah, others came. Right? So first, when I started, I had to figure out how MSM works and have to compile and run with FSL, which is the fmrib software library, I guess. Well, FSL, the Oxford stuff. And I had to make it work on Ubuntu and Mac later when I got my MacBook. And figure out what is in the code exactly. And it seems easy for the first, but you cannot see. Can you see?
Yeah.
Okay. So yeah, because MSM consists of 4 software libraries, or 5 or 6 depending on the viewpoint, but 4 core libraries. So obviously it takes time to figure out how it works, especially it is written in C++. So so yeah. Okay, so the main objective is here, I guess, is to give MSM a software engineering based foundation and how software engineering can assist to optimize and improve the MSM code and the software itself. And for that, I used a few tools. The first one was code cleanup, and there are 2 terms basically for this. One is refactoring. These are basically small, easily reversible changes to enhance maintainability and in general how the code looks. I will show you an example in a moment with a few slides. And the other one is to rewrite certain parts of the code, or certain functions or objects, classes in the code. This is a somewhat larger targeted implementation of the code base, and basically a part of the software needs to be rewritten entirely. Well, in normal practice, and I mean not in research, but in commercial software engineering, code cleanup usually consists of refactoring the code, because rewriting the code is not really make any sense in corporate or commercial software engineering. But here it will make perfect sense. I will show you it in a moment. So targeted rewrites also needs a bit more planning, and MSM needed both, and needs both still in some sense. Okay, so let me show you what I mean by code cleanup. This is a piece of code in the original MSM. Well, I think even if you don't really understand C++ code, this is somewhat confusing for the first sight, and not just for the first sight. I mean, all of the tools that is used here, shared pointers and other stuff, are quite okay. I will tell you about this later. But the outlook of the code was a chaos, somewhat confusing. I don't really want to say anything bad about it because it was working quite nice. But the code, the software was great, but the code itself was a bit chaotic. And if you think about maintainability of a software, if you want to change something in your code, extend it with new features or change a feature, maintainability is a primary importance. So touching this piece of code to change something is extremely difficult in this state of the code. So first, you need to do some formatting. That's really helpful. I even removed a few parts just for the presentation, but it still has some problems. For example, there's a lot of unused variables here. For example, this, do you see my pointer? Can you see my pointer in the, okay. Yeah. So this CI variable is unused here. It won't be in the final program. So today's modern compilers remove these. So it won't consume any resources when you run your program. But again, from the viewpoint of the code, it's extremely confusing. Okay. Also, there are a few other issues here, which is more specific. For example, this is what we call shared pointer. You don't really use pointers in Python because there is no pointers in Python. But this very object here points to a segment of the memory. Okay, so what the creator wants here is to just check whether we provide this specific object to this function. So practically, do we have an exclusion mask or not? You know exclusion mask because you use MSM. But the thing is that if you call this get function, it will copy the content of the pointer here. And this is completely unnecessary because you don't really want to have the pointer itself here. You want to check whether it's provided or not. And it can consume some sort of resources. Okay. So this is very small, but if you call this a lot of times, and in the resampling you call this part, you use this part a lot of times, it can consume some resources. Okay, and also, you don't need to understand C++ for that. So if that condition is false up there, you add 0 to a variable. Well, you know, this is very suspicious. In software engineering, if you see this part of code, you just it will just bug your mind because you don't know what is going on here. Add 0 to a variable can mean nothing, so you can remove it entirely. But sometimes it just, are you sure that, am I sure that I want to remove it? And I removed it and it crashed the code. So, yeah. But anyways, probably just some other values were here. So if the condition is false, then it was added 1 or something, some other value. But yeah, this could be removed entirely, by the way. But again, it was a complete rewrite. Okay, this is somewhat better. I removed the unused variable, removed the part that was suspicious, debugged it, and tried to figure out what is going on. So now it's somewhat better in this. If you see, this is still the original version and the original setup of the MSM. So there is no new tools here, no new anything here. Just removed unnecessary parts and clean up the code. I don't remember exactly, but it could remove the runtime somewhat, just to clean up the code and remove all the redundant branches and statements from the code. So this has had an effect on the runtime as well, and maintainability again. Now this code is much more easy to understand than this one, I guess. And maybe the new mesh library that deals with the resampling and the data types used in MSM, the mesh, the triangle, the point, and so on, look like this most part of the new mesh library. And the new mesh library is a very important part of MSM. Anyways, so it's somewhat better. And just to show you, this is how it looks like now, but I should note that it uses some different tools as well. Okay, and I had to separate resampling of the mesh and resampling of the exclusion mask, because it was merged together, and it was a bit ineffective in a sense that if you have multi-dimensional data, the exclusion mask resampled with all the dimensions over and over again, that is completely unnecessary. But this is methodological one, it's not really important, I had to separate. So the resampling itself is up here, really a few lines of code where you get the barycentric weights and do the resampling according to the bytes. Looks a bit better. Okay, so this is cleanup, and there is another would be helpful software engineering tool that can be used, that is code review. Code review is basically when developers check each other's code. So working in a team, and a developer writes a piece of code, a part of software function or something, and the others review that code and tell you about their faults and what can be improved, what can be changed. Sadly, we cannot do that here, but that would be extremely helpful. But yeah, I'm the yeah, I'm the only one who can code in C++ and have time for this. So. Okay, so we need. So of course, the next step was to figure out something about the performance. And during the cleanup phase, as I mentioned, we could improve the performance somewhat. It's really just like 10% or 20%, not much improvement. So basically, in the original version of my Office PC, this registration took about 90 minutes. It's really a standard registration process. So it took about 90 minutes on my Office PC, and about 30-40 minutes on my MacBook, when I could make FSL work natively on my MacBook, which was great. But anyways, so 90 minutes was the base time that I had to improve. So what are the causes of this then supposedly low performance? Possible the low performance of resampling, the low performance of the code itself. So pieces of the code can be improved with code reviewing or restructuring. And obviously, one major issue was the MSM was running on a simple CPU thread, and that could be improved, of course. Okay, so let's check the resampling. I don't know how familiar you with the resampling, but it involves a step where you need to search for the nearest vertex or triangle on the target mesh, and that involved a distance-based search in the new mesh library, so in the original version of the new mesh. And when you want to get the closest vertex to a point among of tens of thousands of vertices, or even hundreds of thousands, some cases, then can take a lot of time. In MSM, it improved with a pretty smart solution, a smart soft hack. It was improved with a grid. So just a figure here, you can see this point cloud or vertex. You need to find the closest. So what you do is to check each and every point on the mesh and measure the distance. If it's the closest, you select it that's the closest. But again, it involves checking all the vertices in your mesh. As I said, this was improved with a grid. I hope you can see online the grid as well. Maybe the color is not the best, but anyways, first you get the cell with your vertex in and get the neighboring grid cells and search only those grid cells. So the search space was narrowed quite well, I could say. But it's still slowish. So what was the task is to change this to a so-called octree search. And this is a really basic semantic of that, meaning that we create a hierarchy of vertices. So we split the space, the mesh, into 8 equidistant or equal spaces and put the vertices into these spaces. And then if we have more vertex, then we split that part again to 8 and then 8. Okay, so it's like a binary search, but it's an oct search. So we have 8 equidistant spaces. Okay, and this improved the performance. So be it an octree that stores up to 50 triangles, we are not storing vertices now, we are storing triangles in a leaf node. We store 50 right now, but I think it can be improved as well, but doesn't really make a huge difference. Building this octree takes some time. Same as building the grid search, the grid-based search. But search this tree for the triangle is really, really fast. It's for a mesh that has 260K triangles, that is the native mesh. The tree itself is 5 steps deep, so we need to take 5 steps during the search and search that 50 triangles in a vector. And the vector search is very fast itself. So it's just really a few steps. So the time efficiency is really improved in this sense. Okay, and now the resampling takes approximately the same time as in the WB command. It's now under because WB command uses the same octree search approach. Basically, the code in MSM is somewhat the same than in the WB command. I got impressions from the WB command too. Okay. Another thing about low performance, just as I said, low performance of the code. This was the second thing after the low performance of resampler. This function, what it does is that it gives us the angular spacing or the mean vertex distance or mean angular spacing of regular icosahedron. So, or icosphere. So we provide a vertex number, the size of the mesh, and it gives us back the angular spacing between vertices. Okay. From the mean vertex distance, we can calculate the angular spacing. This is the angular spacing of the vertices. Yeah, okay. So how it works is that we provide the number, and based on the number, we set the order of the icosphere. So what is the resolution of the icosphere? We generate the icosphere, rescale it, calculate the mean vertex distance from the icosphere, and from the mean vertex distance we calculate the angular spacing. Generating icospheres can take some time depending on the resolution of that. An order 6 icosphere takes about a few seconds on my computer, 2-3 seconds roughly to generate. But why would we do that? So the mean vertex distance is a constant number for an n-order icosphere. So what we can do is to just return the angular spacing itself. So why would generate an icosphere and why would calculate the mean vertex distance? These are constants for regular icospheres that we generate here. Okay. In this case, we just return a value. We are not generating icospheres, we are not doing anything. Okay, just returning a value. Okay. Of course, this function can be done more concisely as well, and using a bit more sophisticated tools like enums or something like that, but don't want to get into this because this is not a programming course. Okay, so this is another example of the low performance code in some sense. Why would you do something if it's completely unnecessary? Okay, it just takes resources. We have a question.
Quick question, but might not be a quick answer. What is an icosphere?
Oh, an icosphere? Well, actually, we do everything, resampling and all the registration on these spheres, basically. And we generate these. It's a sphere, basically, or a.
Like the represent the surface of the cortex.
Yeah, exactly.
Regular.
So it's a regular sphere, but it's more optimal to generate spheres like this than with point clouds or other approaches. And it's a very good approximation of a sphere. Yeah. Okay. So, yeah. Anyways, this function is completely unnecessary now in the MSM because we are not using angular spacing now. But just for an example of what could we do. Okay. Also, some chaos. These are 5 functions with the same name, but with different arguments. Of course, in this case, these are not the same functions, but yeah, it requires some sort of simplification in this case, and there are a lot of versions of this function that is really unused, and few arguments that are unused even in the original MSM as well. Okay, since the task was also to remove redundant and unused code, I had to figure out what these functions do. But yeah, also some chaos regarding the resampling. So basically, these are doing resampling and projection, point projections. Had to figure out what's the difference and why is it. What's the difference between these functions? These should do the same, but in different way. So yeah, also needed some tidying in some sense. Okay, and also one of my favorite is this the 4 or 5 barycentric functions. The last one is a bit more straightforward. We're getting the barycentric weights for a point, but the others are a bit confusing. So this is also about code cleanup and code review and some optimization of resources in this sense. Okay, and the next big thing was the parallel execution. Old MSM or the original MSM runs on one thread. This is default for C, C++ programs, but I think for most programs, even in Python or any other, environments, you need extra work to parallelize. You need to do something to run in parallel. And the question was, what can be parallelized? What parts of the process, of the MSM process, can be parallelized? And of course, have to do it because just a very simple example is that you cannot run the multi-resolution levels in parallel, of course, because each and every level comes off one after another. Okay, so let's consider this piece of code. It really just about the resampling after moving or deforming the mesh. So you need to get a piece of data here. It's really just about telling you how you can parallelize a piece of code. So what are the problems here? And how it can done? So parallel execution is something like this in a really semantic way. So we have a master thread. We are doing something, for example, reading the mesh from the file is on one thread right now. It can be parallelized probably, but it's a small task, so it doesn't really worth the extra effort. But I will do that. And then comes some parallel regions, some single thread regions, and another parallel region, and so on. Now, these parallel regions can be different things. What I did in MSM is to parallelize for loops. So what we do over and over, parallelizing loops, but you can parallelize other kinds of code as well. Okay. And for that, I use the OpenMP. This is a library for make C code run parallel, or pieces of code or blocks of code. And this is a really simple explanation of that. So let's consider you have a for loop that runs from, well, in this case, 1 to 13, 1 to 12. And this will put three different threads, create three different threads, and each of the for loops will be on different threads. So this will be the first four, the second four, and the third four steps of the loop on different threads. Okay. So this is maybe the basic OpenMP parallelization process, and in most cases, this is really the basic parallelization. Okay, so back to the code, and I highlighted the block that can be parallelized in this case. So what is going on here is that we're getting the source data, we get the closest triangle for that, resample the data, and store it probably somewhere. Okay, so yeah, this part is the closest triangle search, and this is the resample part. Okay, what are the problems here? So if you run something on a multi-thread or multi-process environment, you are still using the same memory, the same variables, right? And if your processor wants to access the same memory from multiple threads or multiple processes, that can cause some problems, can cause some issues. So one thread tries to write it, the other one to read it, and multiple threads try to write the same memory segment in the same time. That can cause huge confusions, and well, what you will experience is that you get an error called segmentation fault in the terminal, which is in C and C++ is the worst, one of the worst error messages. But anyways, so these are variables here, or memory segments, we can say, that is accessed with multiple threads in the same time. Also, a question is that what this function does. So is it a problem that it's here, or what is going on here? Now, on the next slide, I just pop this out. So this, I just moved the function here. So it's not a function anymore. It's done locally. And I can see that here's another problem. Now, if you want to create something in a multi-thread, multiprocess environment, you need to figure out how your data structures work. There are data structures that are thread safe, and there are data structures that are thread unsafe. Now, this is a vector, a simple vector, that is what we call it thread safe. But also you need to figure out and pay attention whether the operation that you do on these vectors are thread safe or thread unsafe. And the pushback function, with which you can add an element to the end of your vector, is a thread unsafe. So it's not thread safe operation. The pushback only adds the variable to the end of your vector. Okay. In short, the problem with pushback is that it changes the memory allocation over and over. So if you fill your vector and you call a pushback again, it will change the allocation, so it moves all the vector to a different memory space, and so it touches the memory. And it's not a good idea to do that in a multi-thread environment. But it can be removed. So make your variables thread local. So move all the variables, all the memory operation into your thread. What is going on here? What is inside the multi-thread block, in this case inside the for loop, is a thread local. So each and every variable exists only inside the thread that you use. So every thread has its own variable, own memory allocation. And you solve the problem. How can you solve the vector problem? Well, in this specific case, we know the size of the vector. We know how many elements we will have in the vector. So we don't need to use pushback to change it over and over. We can set it before we go multi-thread. So we can set the size of the vector basically in the single thread, the master thread part. Okay, so here you set the size of the vector and access the element directly. Okay. I'm pretty sure you're familiar with this one, so it's nothing problem. These vector accesses are direct accesses. It's okay. Anyways, this was in a previous version of the newMSM. Since then, I moved the parallelization one level up, so it's a bit more optimal in this sense, because it's really important that what you do on one thread. So in this case, it can happen that in the range of the source vertex, you only have a few nodes that you want to reassemble, 4 or 5. So what you do here, in the case of 4 or 5 elements, that you just use 4 or 5 threads, which is not much, I can tell. And this work that you want to do here is also not really worth the effort to parallelize. So you need to have a lot of work to do on a thread to make it worth to parallelize. Okay, otherwise it wouldn't be good. The FSL has this issue with some OpenBLES library, I guess, and they disabled OpenMP entirely from FSL because of that. It even reduced the performance of some operations because of this. Okay, yes?
Yeah, I just have a question, like in general, like say if I had my code and I want to like parallelize it, how do you decide if something is worth, like do you just check like
well, you can.
Time it's taking and like how do you decide if it's worth parallelizing?
Well, actually you can measure that how long does it take, but as in software engineering we usually just try it. Of course, there are advanced debugging tools for that. Those tools that I didn't use here, but in most cases, parallel programming is a lot of testing and measurement. I had the sense that this is not optimal here, especially on high resolution meshes and high resolution icospheres, because this sourcing range, the size of the sourcing range is not big enough first. And also this part, the body of the block is quite short in the sense of processing. Okay. So measurement is the best that you can do. Okay, and also validate. So you can see that it is running on multi-thread, and not just this. Of course, you have this resource monitor on your Ubuntu, and some sort of resource monitor on your Mac, but that is not really helpful in most cases. So you can use this, and we can also validate based on the temperatures of the BH. So the temperature went up a bit around my desk when I finally made it work. Okay. Moving on, there were some good tools already in use in the original MSM. Most of you are probably not familiar with this, but C++ reference type, shared pointer for passing and checking, and other C++ tools. So it was really, in this sense, a modern code. But some were also missing, like move semantics that can improve a few things. Now it's there, so memory management and memory operations somewhat better also. Okay, and all this resulted in the new resampler library, and this contains new resampling methods with the octree search, and removed a lot of unused code like the thin plate spline-less resampling, thin plate spline resampling, the grid search that I mentioned earlier, some Gaussian-based interpolation, but some parts of the code were reused because those were written quite properly, like the barycentric rate calculation. It was quite optimal, just had to parallelize it, and added some demo code to test surface and data resampling that you can use also if you want. It's in the repository. Okay. So the next step is, now we have a great resampling library. We need to include it to the optimization library. So basically move all the features that use the old resampling, the new mesh library, and use the new resampling library. And for that, of course, it requires some code cleanup, also remove the unused code, remove code that is not working, which was interesting, but there were some parts that were not working, and switch out all resampling code to the new one. And that was a bit of a work, I can tell. Okay, so resampling, relations, nearest triangle search all need to be removed, either removed or changed. Okay, so the new optimization library, remove code that is not working. For example, the NMI similarity metric, which was interesting, or the affine method use the SSD metric only. There were some unused parameters that remained in the code from old versions, even older than the old version of the MSM, like the AKNN or scaling and so on. And also improved with parallelization. Right now, only the hook method using parallelization for the nonlinear, and the FI method using parallelization. FastPD is not using because it's fast, so it doesn't really require any parallelization at all. At least on lower resolutions, I guess. Okay, what was? Yep.
Is the NMI metric not used because you just don't decide to use it? Or
Specifically the NMI wasn't working at all.
it wasn't?
So I tried it with multiple test cases, and it just crashed the program entirely. So that was a piece of code that wasn't working, but for example, this AKNN option, it wasn't used. So the parameter was there, and the program read the parameter, but nothing happened. So it was a loose end in this sense. I think I haven't removed any parameter or option or tool that I think is used. So I won't remove anything based on my decision that, oh, I could remove the FI method because I don't like it. So it's not how it works. If you think about this, I won't do that. Okay. So the major boost, I think, in the MSM was the part where we do the resampling in the optimization library. In the original version, this was the closest triangle search, and this is what involved that grid search algorithm, or grid-based search. Just to show it to you again, just a reminder. So it used this, and now it uses the closest triangle search using the op3. And this is really a major boost in the MSM. This is much faster than the previous. I'm not saying it's much more accurate or much more, not much more accurate. It's just really faster. Okay, so about the current performance, the same process takes about 2 minutes on my PC and about 1 minute on this MacBook. After I figured out how parallelization works on MacBook, because this is an entirely different architecture. So these Apple Silicon, the M1 and M2, and these Macs, based on an entirely different architecture than the desktop computers or the Create cluster you use daily. So after I figured out how it works, and the FSR now is natively supporting Mac, I can make it run in 1 minute. That took 90. Well, on the yeah, no, there's still a lot of work to do with it. So yeah, so about performance, I think it's closing to an optimal state. At least my Office PC is overheating, so I'm satisfied with that. When your PC is overheating, you can say that you are using your CPU. Anyways, it still needs a lot of testing, but I will get to that in a moment. Okay, so needs what is on currently and what we need, so that it needs debugging, of course. And I have a few test cases that you sent me, and I test against these test cases all the time. I can visually check. I will show you in the end an example what I mean about visual check, but of course the small differences or the small errors I cannot really point out. I cannot really spot. You are the expert. I'm just a software engineer. Okay, so I do the make the software, do the tests, but you need to validate the results. If you're satisfied with it, we can move on. Otherwise, I need to work on that. Okay. Also, this is the same for the ACP pipeline. We are testing it. It is currently running on my Office PC as well. Well, it differs from what we expect. So of course, it needs some fine tuning and fixing, and needs more testing. Testing is very important in this case. Okay, so what am I working on currently? To switch out the Hawk and the FastPD for free libraries. This is a kind of a business decision. These libraries cannot be included in the commercial version of FSL. So we need to remove Hawk and FastPD. And now I'm trying to make it work with the Markov chain Monte Carlo method. It won't be as fast as Hawk or FastPD, I can tell, because these Monte Carlo methods are usually very slow. But anyways, maybe we will try to make it work on GPUs, and that can improve this performance a bit. So this is the next step. And later, in any order, to rebuilding AMSM, of course, important is the group-wise registration. I think during the summer I can start working on group-wise registration and some low priority tasks, re-implement NMI, and there were a few wishes from the American guys as well. But yeah, and needs more testing. Testing is very important. Okay, and just an image at the end. Well, this is what I mean when I say visual confirmation is. Yeah, and yeah, so this is a product of the new resampling library from October or November, something like that. Anyways, thank you for your attention, and thank you for having me.
Well done, Renato, showing up my terrible, terrible C++.
It wasn't terrible. It was just missing the final steps of software engineering, which is code cleanup and code review.
Yeah, I mean, this is why, like all of FSL, you know, when the Esper goes, it doesn't matter if things take 3 million years to run. That's because, you know, physicists and mathematicians code it and not software engineers.
Yeah, exactly. And research takes time, they used to say, but right now MSM is more of a supervisor-friendly software rather than a student-friendly software, because right now, or so far, students can say, it takes a lot of time to run MSM in 90 minutes and 2 hours, but now it runs fast. So yeah.
Very, very cool.
Okay, so it wasn't my goal to point out that your code is not doesn't look good.
I'm pretty sure I said at the outlet that it was bad. I have literally no idea. You know, like every now and then you go, Emma, why is there this thing in the code? I'm like, no idea.
Yeah, that's accurate. But it was a long time ago. I can see the copyright text saying that you started like in 2012, and maybe the most recent code is about 2014 or something. So I no wonder you don't remember most of it, because I cannot remember what I wrote 2 months ago. So
no, well, AMSM was put in 2016, but yeah, it was a long time ago. But it's that thing where, you know, you never, I mean, I didn't even use proper version control of it of any kind until quite late. So you don't go back and clean anything up. But yeah. But yeah, so now it runs in a minute. Whoop, whoop.
yeah. Okay, so
But then, like, that's following up with what Renato said. Can we all please help him test test it. You're all running it. You've all run every time you run newMSM, and I know a lot of you are doing it, you have to run old newMSM and check how close the results are and feedback.
Yeah, that would be nice. So I would suggest to, if you really use MSM for something, just use the new one as well. I think most of you run MSM on Create, I guess. Now you can run it on your computer as well. And I bet it will finish faster on your own computer than the old MSM on Create. You can specify how many threads you want to use. Of course, if you specify that you want to use all the threads in the computer, don't expect that you can do anything else besides that, because you won't. But you can specify use half of it or something like that, half of your available threads. But it would be really helpful and important to have feedback from all of you who use MSM. AMSM as well. AMSM is a bit weird, and I'm still trying to figure out some parts of it. But we need to rebuild it either way, I think. So, but yeah, it would be nice to have. I just 2 weeks ago I found a bug using AMSM, for example. It was my bug, not yeah. It was no. It was my bug, not AMSM bug. But I found it using that, so it would be useful to have some feedback. Okay, I'm just